Good afternoon, everyone. My name is Zhongrui from the University of Electronic Science and Technology of China. Today, I will present my work, a composition method of capacitive angle sensors in ultrasonic motors during start and stop stages. This talk focuses on why angle result becomes unreliable exactly when MEMS ultrasonic motor starts and stops, and restores accuracy so closed loop standing becomes feasible. First, an ultrasonic motors has three main parts: the stators, the rotors, and the capacities. We apply voltage to the ceramic. The inverse capacities in fact make the stators vibrate. The vibration can be a standing wave or a traveling wave. Points on the stator move in small ellipse. Frictions from these motions drives the rotor to the spin. Ultrasonic motors has clean advantage: small size, fast response, and loss weight. So they are widely used in aerospace engineering, optical engineering, and micro robots. Our motors is built on a silicon-based MEMS process, compatible with micro nano, fiber and enabling high-yield system-level integration. Compared with the conventional ultrasonic motors, the MEMS route offers clear benefits, such as smaller size, mass produced with lower cost. Higher integration is of area implication and high machine accuracy. When we apply AC voltage, the PCT plant expand and contract again and again. This comes from inverse PCT effect. This excites to start vibration mode that is orthogonal. Next, we cite their physics and altitude. If the spatial phase shift is 1/4 of lambda, the time phase shift is 1/2 of pi, and the amplitude is a quarter. Then a traveling wave from on the stator by the Capacitive plate series points on the stator's surface moved in small electrodes. As a result, friction from this motion drives the rotor to turn. Mechanically, our support departs from central grid support. The general approach offers low ankle loss but needs flying leads like constant rotor assembly. Our approach uses an outer ring, flexible support for easily routing, plus sealed point support that further reduce anchor loss. Open loop starting on MEMS traveling waves, ultrasonic motors can be imprecise with a maximum step angle error can reach about 1.11 degree in our experiment. For high present precision, we need a reliable angle feedback. It must remain trustworthy during start and stop. The two most dynamic phases before. Before synthesis, a quick note on drive dependencies. The usable voltage frequency range is relatively narrow. Phase difference influence need non-linearly. Voltage amplitude correlated with the speed approximative linearly. So we use the the half difference to control the difference. We use the voltage and the amplitude to control the speed. It follows for angle sensing. We use a capacitive method. It follows the parallel applied capacitive principle. A top electrode is placed on the rotor. A bottom electrode is placed on the stator. The bottom electrode is split into two groups, A and B. When the rotor rotates, there is a corresponding change between the upper and the lower surface on the stator and the rotor. The opposite area between the corresponding electrocouplant changes, and the capacitance value will be also changed accordingly. Next, let's look at the output signal of the capacitive angle sensors. Figure shows that layout of the single electrodes. The bottom electrode is split into two groups, A and B. When the rotor is at theta 0, group A has the largest overlap and the top and largest overlap with the top electrode. Group B has zero overlap. So the capacitance from group A is at its maximum, and the capacitance from group B is 0. As the rotors move to theta 1, the overlap of group 1 decreases, the overlap of group B increases. Their area increase has the same shapes, but the shifting in phase. With the rotor reach theta 3, the capacitance from group B is at its maximum. The capacitance from group A is 0. Finally, at theta 4, the two signals form the same as theta 3. The range from theta 0 to theta 4 is one period of the capacitance angle changes. In addition, taking the difference of the two capacitance signal increase the two output and reduce noise. Of course, our angle sensors has some issues that can cause errors. In text, the mirrored waveform is not same as the ideal one. This may come from even speed or a small tilt between the stator and the rotor. Even so, the match is better near the peak and the peaks and stops. We can also reduce mounting errors by adding more peer load. Finally, during the start and stop, the traveling waves groups from 0. At the same time, the rotor keeps turning, so both the overlap area and gap change together. This reduces the accuracy of the angle calculation. Uh, to fix this problem, we add compensation during start and during stop. First, in the start phase, a traveling wave comes from two standing waves. We excite the first standing wave. It lifts the rotor to a stable height. Then we excite the second standing wave. Together, they form a traveling wave and drive the rotor to spin. Next, in the stopped phase, we change the theme of the phase difference. It changed the rotor's direction briefly. It shortens the braking distance. It also improves the accuracy of the angle sensors. Finally, we built experimental setup to test our comprehension method. As you can see, the capacitive sensors become more accurate during both the start and the stop phases. Finally, this is my conclusion, and well, thank you very much.